Okay, so the last one that we're going to do is the cotangent function, and that is the last reciprocal function that we're going to do. So we did secant, cosecant, and now cotangent. After that, the only thing left that we have to do are inverse trig functions, so that should be tons of fun. Okay, so let's look at cotangent. Cotangent is defined as 1 over tangent, obviously. So obviously you probably know what we're going to do next. All of the values of x that are multiples of pi, tangent of x is equal to 0, and cotangent of x is undefined. So pretty much wherever tangent is 0, cotangent is undefined. We already knew that from the previous two. So we're going to graph tangent and cotangent on the same set of axes and see what happens. Now, I know that you've only done the graphs of tangent a couple of times, so let's do that together for the first time. So we are at pi over 2. Pi, 3 pi over 2, and 2 pi. Now just remember that tangent is undefined at 90, which is pi over 2, and 270, which is 3 pi over 2. So right here and right here, those are two vertical asymptotes, meaning that tangent is not going to pass this line, and it's not going to pass this line. So if you want to draw in those vertical lines during the test, that's perfectly fine. Now tangent starts down here at 0, and it's going to extend upward, but it's not going to hit that vertical asymptote. Now it's going to start all the way down here, pass through 0 at pi, and then keep going towards this vertical asymptote. And hopefully yours are a little bit more neater than mine, and then the same thing again. It's just a pattern that keeps going and going and going. Okay, so that's what tangent is equal to. So now this is what cotangent is going to look like. Wherever tangent is 0 is where cotangent is going to be undefined. So see how tangent 0 right here? That means that cotangent is going to be undefined right here. Because tangent is 0, cotangent is going to be undefined right here. Because tangent equals 0, cotangent is undefined right here. So it kind of gets just a little bit confusing. So what I'm actually going to do is just going to graph it for you on the graphing calculator, because I think that's just easier for you to see anyways. So cotangent is 1 divided by tangent of x. We're going to graph that. And you see how tangent and cotangent look really, really similar, but the difference between the two is that tangent goes up and curves like this, cotangent curves the other way. So it's just, you're not going to ever have to graph cotangent, but you are going to have to recognize it. So personally, honestly, what I would do is put it in your graphing calculator and play the matching game. Just match up whatever picture goes with that one. So that's why I didn't really want to draw it on this graph, because there's just a lot of stuff going on, but this is what cotangent looks like. So it gets really close to this asymptote, crosses through 0 right here, and then comes down. It's really close to this asymptote, crosses through 0, and comes down. Okay, so it's kind of just moving backwards. And then this is the next homework assignment, and we are flying through all these homework assignments, John. So as long as you're watching these videos, then you should be able to complete these assignments, and you should be like really, really good on track. I can get you through all these chapters in the next couple weeks as long as you're staying with me and watching all these videos. So let's see what else we have to do. Graphs of inverse trig functions. Okay. Now, when Miss Tompkins did this stuff in class, what she did was had you guys watch this like weird video on some website called like TeacherTube or something, and it had this guy and he was yellow and he kind of looked like Bart Simpson, and he had like a weird southern accent and it was very strange. And I'm not going to put you through that. Here's what I'm going to do instead. See, that's what the video is, but hey, if you want to type all that in and go online and watch it, be my guest. Okay. To form the inverse of a function graphically, you reflect over the line y is equal to x. Okay? If you were to find the inverse of an equation, you switch the y's and the x's. So that's why if you're finding the inverse of an equation graphically, you flip it over the line y is equal to x, because you're doing the same thing. You're just flipping or switching those x's and y's. The only thing that you need to be careful of is when you flip it over the line y is equal to x, you have to make sure that your inverse is still going to be a function. And a function means that it passes the vertical line test. So in order for the inverse to pass the vertical line test, that means that your original function had to pass the horizontal line test, okay? Because we're going to flip it. So horizontal becomes vertical. So if you take a look at a graph or a picture, don't read that. If you're going to take a look at a graph or a picture and it fails the vertical line or the horizontal line test, that's not what I want. If this is a function, and let's look at a parabola. How about a parabola? Because parabolas are easy. This is the picture of a parabola. And this function or this graph quite clearly fails the horizontal line test, because if I draw a horizontal line, it passes through that line 2 points, here and here, so it fails. So that means that if I were to draw a picture of the inverse of this function, when I flipped it over the line y is equal to x, it would look like this. This is what the inverse of a parabola looks like this. See how it's a parabola on its side? So because this parabola failed the horizontal line test up here, that means that down here its inverse is not a function, because functions have to pass the vertical line test going straight up and down. And because it failed it up here, that means that it fails down here, and this is not actually a function. Okay, functions have to pass the vertical line test. Well, we're going to find the inverses of trig functions, and obviously we want them to be a function, right? We don't want to, talk about things that aren't functions. So we just need to make sure that they're actually going to be functions. So what we're going to do first is I'm going to graph. Let's deal with sine first. How about sine? Sine's easy. I'm going to graph the sine function. And I'm not even going to make it, specific. I'm not going to, go through and label all my axes. That's what sine looks like. Now, if I were to extend this curve in the other direction, it would look like this. And you can see that if you look on your graphing calculator. So this is y is equal to sine of x. Okay, well, if I'm interested in taking a look at what the inverse of sine looks like, and we write it like this. We write y is equal to inverse sine, and you denote that with like this little -1 exponent up there. That means inverse of x. Okay, well, if I take a look at the graph of sine, does sine pass the horizontal line test? And hopefully you're saying no. Obviously it doesn't, because it fails here and here and here and here. It would only pass the horizontal line test if it passed through that line one and only one time. So, alright, sine fails the horizontal line test. Does that mean that the inverse of sine just doesn't exist? Well, no, not exactly. And this is what this Bart dude was talking about in his video. Just because it fails the horizontal line test doesn't mean that we have to stop there. Doesn't mean that we can't have an inverse. What we're going to actually do is, because we can't analyze what the entire sine curve looks like, because it continues on for all, in both directions, we're not going to look at the whole sine curve. What we're going to do is something called restricting the domain, or restricting the x's. Instead of looking at all of the x's, we're only going to look at a couple of them. And if we only look at the x's in this tiny little range, then it'll pass the horizontal line test. And let me show you what I mean. What if, instead of looking at all these x's, what if I only look at the x's between -pi/2 and +pi/2? And I'll show you why I picked those x values. What if I only look between here and here? So I'm only looking at this small little section of my sine curve. That's the only part that I'm going to consider. I restricted the domain. Restrict domain. Okay? And if I only look at that little section, does it pass the horizontal line test? Yes, because it only passes through that horizontal line at one point right here. Awesome. And because it passes the horizontal line test, that means that when I flip it over the line y is equal to x, that the inverse is going to exist. And here's what the inverse of sine of x actually looks like. Flip it over, actually, and I always have to like look at it sideways to figure out what it's going to look like. It only looks like this tiny little section right like that because we flipped it over the line. And don't even ask me how I've memorized what that looks like, but you could always just put it into your calculator like this. Y is equal to, and how am I going to get that button? You see how right above sine it has sine to the -1? That means the inverse of a sine. So if I hit second sine, it's actually going to graph the inverse of sine x for me. And I'm going to change my window to be -2 pi to +2 pi just so I can see on both sides of those axes. I'm going to graph it. Okay, so see how it just, did I draw that upside down? I guess I drew that upside down. Hold on, let me change my window. Let me change something right here. I'm going to change this to -pi/2 because that's where I restricted my domain. Enter. +pi/2. And it's very, very possible, John, that I just drew that wrong, but I just want to double check. I'm going to make my x min -1 and my y min +1. And graph. Okay, so I drew it wrong. Everybody makes mistakes. Okay. So let me put this over here. And then let me try to draw this correctly this time. Okay, so it actually looks like this. Yeesh. Okay, it should look something like that. Yet again, you will not ever be responsible for actually drawing this yourself. All that you will be responsible for is matching. So if you have a picture that looks like that, then you have to match it. Okay, that's it. So that's what the inverse of sine looks like. And then let's go to the next page and talk about the inverse of cosine. And I don't want that. I want this. Oh, I know what I missed. I forgot one thing. So you're going to see maybe questions on the test, and it's going to say, you know, in order for the inverse of sine to exist, what does the domain and range have to be for sine? So we restricted the domain, so the domain of sine, instead of all real numbers, is between -pi/2 to +pi/2. And then the range is still just between +1 and -1. Because that's how high and low it goes. Now, when you flip it over the line y is equal to x to figure out what the inverse is, the x's and y's switch. The domain and range switch. So your domain of the inverse of sine of x is between -1 and +1. And your range is now between -pi/2 and +pi/2. So that might be something that you want to write down in your notes, just because I've seen questions like this already on the Trig Regents review that we're doing, so just be careful of stuff like that, okay? I'm going to stop this video and start another one for you.